Hello there. Here's an additional example of showing that a proposed solution to a recurrence relation really is a recurrence relation. I'm looking at the recurrence relation an equals an minus 1, the entire thing plus n if n is bigger than 0, and it has an initial condition of a0 equals 4. Here are the first several terms of this sequence. And I'm going to claim that the function f of n equals n times n plus 1 over 2, the whole thing plus 4, is a solution to this recurrence relation. Where this function came from is discussed in the book, but the point here is we're not going to talk about how to generate this solution. We're just going to take a proposed solution and check to see that it really is a solution. Now, if I take this function and plug several values into it, starting at 0, then 1, then 2, then I get this sequence of outputs. And that does agree with the terms of the sequence. However, as we discussed in the earlier video, that doesn't necessarily mean anything. That just means that this might be a solution because it doesn't disagree yet with the recurrence relation. To prove that this function really is a solution to the recurrence relation, I've got to do two things. I first have to show that the function satisfies the initial condition. That is, when I plug in 0 to the function, I get the same thing as the initial condition a0. And then I need to do an algebra-style argument to show that the function itself satisfies the recurrence relation. So let's dig in and do each one of these one at a time. Satisfying the initial condition is fairly easy to show. The initial condition is a0 equals 4. And I just need to take my function and plug in 0 and check to see that the output is 4. Well, the formula says I take the 0 and I compute 0 times 0 plus 1 over 2 plus 4. Now this fraction here just evaluates to 0 because I'm multiplying through by 0. And so the entire result here is 4, and I see that the initial condition is satisfied. F of 0 is the same thing as a of 0. So the function will produce the correct first term of the sequence. Now, to prove that the function continues forever to produce correct terms of the sequence, I can't just plug in specific numbers. I need to actually use the function itself and show using algebra that no matter what the input is, the same rules of term generation given by the recurrence relation will be satisfied by the formula. So I'm going to copy down that recurrence relation again, an on one side, and then make a visual clear separation and put the right side over here, an minus 1 plus n. And I'm going to replace all terms of the sequence here, which in this case would be the an and the an minus 1, with their corresponding function outputs, and just see that the left-hand side equals the right-hand side. So let's start on the left-hand side and work with that in isolation. I have just an, and an I'm going to replace with fn, f of n, and that's got a formula that I'm just going to copy down, n times n plus 1 all over 2 plus 4. That's the full left-hand side. Now let's move over to the right-hand side. I'm going to replace all the instances of the sequence terms with their corresponding function values. That's only one of those over here. That's an minus 1. I'm going to replace that with f of n minus 1. And I happen to have this plus n that continues from the previous line. That's not a term of the sequence. That's not an a sub anything. That's just a variable n. And so it does not get replaced by anything. So now let me use the formula. When I compute f of n minus 1, what that means is I'm going to go to my formula, which is up here, remember, and I'm going to replace all n's with n minus 1s. And so here's what that's going to look like. The first n, that's right here, I'm going to replace with an n minus 1. And the second n, which is right here, I'm also going to replace with an n minus 1. And that is being added to an existing plus 1. So it's n minus 1 plus 1. And remember, that is all over 2. And then there's a plus 4. And then there was also this plus n that came from here. So the expression here in the green is what I get when I take f of n, which is this whole formula right here, and replace each instance of n with an n minus 1. Here's the first n minus 1, and here's the second one. So if that makes sense to you, congratulations. If you're kind of struggling to understand this, pause the video, replay, and before you hit replay, try to work it out yourself, and then ask questions about algebra if you need to. So let's proceed and try to simplify as much as we can. What we're hoping to see is that after simplification, the right-hand side over here should equal the left-hand side over here. Here's the left-hand side's result. The right-hand side doesn't look like that yet, but we have a lot of simplification to do. So let's keep working here. This fraction can do one quick simplification, n minus 1, and then on the inside here, there's a plus 1 and a minus 1 that cancel out. So that's actually just an n over 2 plus 4 plus n. All right, so I'm going to move my screen up just a little bit to get some more room. I'm noticing that I see a plus 4 on the left-hand side, and there's a plus 4 on the left-hand side. So I'm actually going to focus on simplifying what's left. That would be this term here and this term. If I add those two together, what do I get? Well, let's see. I can simplify the fraction here in this first box by multiplying the n through to n minus 1, and that would give me n squared minus n over 2. I'd like to add n to that, so I'm going to move that around, and then I have this plus 4 that's left over, just moving it to a different place. Now let's see what I can do with adding these two terms together. I'm adding a fraction to something, and so I'm going to get like denominators, get common denominators here. I have n squared minus n over 2, and then instead of n, I'm going to write 2n plus over 2, so I can add the two together. Now let's add those two together and see what we get. I have n squared minus n plus 2n over 2. And remember, there's a plus 4 that's left over. And I see a simplification I can make right here. This is now n squared minus n plus 2n is a plus n over 2 plus 4. That's an n. All right. And now one last step. Does this equal what's on the left-hand side? Well, it doesn't look exactly like it, but if I do one extra step over here on the left and multiply the n through the parentheses, I get n squared plus n over 2 plus 4. And now that is exactly equal to what was on the right-hand side. So what does this prove? This proves that the function f of n that's in the green up there, a proposed solution, really is a solution to the recurrence relation, because when I evaluate the function n on the left side of the recurrence relation, and then evaluate it on the right side of the recurrence relation, the two expressions that result really are equal to each other. And so that means that the function satisfies the same rules of recursion that the original recurrence relation does. And so therefore, since it agrees on the initial condition 2, it's going to produce all the same terms of the sequence forever. And that is another example of proving that a proposed solution really is a solution to a recurrence relation. Thanks for watching.